Welcome back, our dear students of Senior 4. This is the current electricity series, and this is the third part 3. I'm still your host, Mandy Dennis, and I encourage you please to do all the exercises, even in the episodes before the first 2 parts. Please, I'm still waiting for those who haven't handed in their answers. Let's dive into the third part. Now here we want to see the expressions that we can use to get the currents that divide at certain junctions. So let us look at this case where we have current I dividing or splitting into I1 and I2. Which formula can we use to get I1 and I2? Now the formulae are very simple. To get I1, the current that flows through R1, you get R2 over the sum of the two times the current that came. Similarly, if you want to get I2, the current that flows through the second resistor, you will get R1 on top over the sum of the two resistors times the current that came. Please, this applies only for two resistors in series. Observe these, study these formulae, please, and don't quote them wrongly. If we are using I1, if you want to get I1, R2 has to be on top. If you want to get I2, R1 has to be on top. Look at this example. We have a current of 2 amperes that splits up into I1 and I2. So the question says, determine the value of I1 and I2. Now, let us call the 3 ohms resistor R1 and let us call the 5 ohms resistor R2. So, remember from our formula, I1 is equal to R2 on top over R1 plus R2 and then times I. Our I is the current before it splits up. And then this is the one that goes through the 3 ohms resistor is I1, through the 5 ohms resistor, that's I2. So we shall have I1 is equal to, what is R2? That will be 5 over the sum of the 2, which is 8, times 2 ohms. And what does that give us? With your calculator, you realize you get 10 over 8. 10 divided by 8 gives you 1.25 amperes. So now we know that our I1 is 1.25 amperes. So what will be I2? Now if I was 2 amperes and then split up into 1.25 and then the other, that means to get I2 here, you will just get this 2 minus 1.5, and that should give you 0.75 amperes. You can actually use the other formula. So we have said that I2, we got it as 2 minus 1.25. And this gives us, sorry for my hand, can't write well. So we are getting 0.75 amperes. Using the formula, you can still say I2 is equal to R1 on top over the sum of the 2, then times I, which will be 3 over the sum of the 2 is 8 times 2, which is going to give you 6 over 8, which is same as 3 over 4, which gives you 0.75 amperes. Okay, let us look at how we treat a voltmeter when it's connected in a circuit. So voltmeters are used to measure voltage, and that is PD or EMF. Voltmeters have very high resistances, and for that matter, therefore, almost no current passes through them. So when a voltmeter is connected in a circuit, almost no current passes through it. And because a voltmeter draws no current, because of its very high resistance, so it's connected across the cell or across a resistor. We call it parallel connection. If you are connecting a voltmeter, you connect it in parallel with a cell or in parallel with a resistor or a conductor whose PD is required. We're going to look at cases where we will be using a voltmeter. So when a voltmeter is connected across a cell or a battery in an open circuit, it reads the EMF of the cell. So an open circuit. What is an open circuit? An open circuit is a circuit in which the battery or the cell delivers no current. That means the switch is open in simple terms. So no current flows in an open circuit. Look at this case. Here, a voltmeter is connected in parallel with the cell. The switch is open. So in this switch, here, if the switch is open, you realize that in this circuit, no current is flowing. Therefore, this qualifies to be an open circuit. An open circuit is a circuit in which the cell or the battery delivers no current. So when a voltmeter is connected across a cell or a battery in a closed circuit, it reads what we call the terminal PD. It reads what we call the terminal PD. This is a closed circuit, and a closed circuit is a circuit in which a cell or a battery delivers a current. So the terminal PD of the cell is always less than the EMF. We shall see the difference between the two because it has also a special name. If a resistor is connected in series with a cell and a voltmeter is connected across the ends of the resistor, the voltmeter reads the PD or the voltage across the resistor, which is equal to the terminal PD of the cell if there is no other external resistor. I'll explain better with this diagram. We are saying if a resistor here, if you look at this resistor connected in series with this cell, they are in series, and a voltmeter is connected across the terminals of the cell or in parallel with the cell. So the voltmeter here will be reading what we call terminal PD, because connecting these terminals here, connecting the terminals of the voltmeter here and here is equivalent to connecting here and there. It's the same thing. Please think about it. This is a voltmeter. If here the switch was open, supposing we would break here, no current would flow. So the voltmeter would only read the EMF of the cell. Now that here the circuit is complete, the switch is closed, that means that the current is flowing. So this is a closed circuit, and the voltmeter here will be reading from, if you look at this, the terminal here is this point, and the terminal of this resistor is this point here. So this voltmeter here will be reading the terminal PD, which is the PD, which is going to be the PD across the external resistance or external resistance of this circuit. You can also have this case. Look at this case where we have changed and we connected this voltmeter across just the terminals of the resistor, external resistor. In both cases, we get the terminal PD. So here, I told you that if this is our voltmeter, connecting the terminals here and here is the same as connecting here and here. It is the same thing. For as long as the current is flowing, the voltmeter will read the terminal PD, not the EMF. It only reads the EMF when the switch is open. The EMF of a cell is the energy provided by the cell or by the battery per coulomb of charge passing through it. That is in many cases called the work which is done to drive which is done by the cell to drive one coulomb of charge through the circuit in which that battery or the cell is connected. In other words, you can define EMF as the PD across the terminals of a cell or a battery in an open circuit. Students always like this because it is shorter, but still, this is also easy for you to remember. The PD across the terminals of a cell in an open circuit, that is called EMF. So the SI unit of EMF is the volt. Remember, EMF and the PD, they're all voltages, and the SI unit of voltage is the volt. Okay, terminal PD, which we quote by V over cell. This is the PD across the terminals of a cell in a closed circuit. So terminal PD of a cell is always less than its EMF due to the internal resistance of a cell. What is now internal resistance? That is the opposition to the flow of current within the cell due to the chemical composition of the cell. Now remember that cells have chemicals in them. Because of those chemicals, there is always the opposition to the flow of current through the cell itself or through the battery, and that's what we call the internal resistance, the opposition to the flow of current within the cell or offered by the cell due to the chemical composition of the cell. Now, numerically, the difference between EMF and terminal PD is what we call the lost voltage. So when you get EMF minus V, which is the terminal PD, you get the lost voltage. Lost voltage is defined as the PD across the internal resistance of a cell. Okay, what are the factors that affect or determine the internal resistance of a cell? Number one is the surface area of the electrodes, the distance of separation of the electrodes, the nature of the electrodes used, and the temperature and concentration of the electrolytes. So I will request you to research, find out how do each of these affect the internal resistance of the cell. How do we connect ammeters in circuits? Now remember, ammeters measure current, so they must allow as much current as possible to pass through them. Therefore, they must have the least resistance possible. And for that matter, therefore, they should be connected in series so that all the current passes through them, all the current that's available for measurement. Ammeters are used to measure current. Ammeters and other current measuring instruments like galvanometers, milliammeters, and others have very low resistances and thus offer very low or no opposition to current flow. They are therefore connected in series with a cell to measure the current it supplies, or in series with a resistor to measure the current that flows through that resistor. Look at this case. If you want to measure the current that this cell here is driving or is sending, you will have to connect this ammeter in series with the cell. So here it shows you that the current that it's sending from the positive terminal I flows into the resistor here. Remember, no current goes into the voltmeter. Why? Because it has very high resistance. Exactly. So the ammeter has to be connected in series with a device if you want to determine the current that flows through that device. I hope the English is right. And if you want to determine the current that this cell is delivering, still you'll have to connect the ammeter in series with it. Let's continue. So how is EMF related to terminal PD and the internal resistance? So there is a simple formula. We said that EMF and terminal PD are different in value, and the difference between them gives the lost volts. So EMF is equal to terminal PD plus lost volts, which we can write as EMF is equal to terminal PD plus lost volts, IR. Yes. Remember, we define terminal voltage as the PD across the internal resistance of the cell. So that is the current flowing through the cell times the internal resistance. This is the terminal PD. The PD across the terminals of a cell in a closed circuit. This is the EMF, the PD across the terminals of a cell in an open circuit. Okay, now let's simplify. We can write this as EMF is equal to IR plus IR. I capital R plus I small r. Don't forget this. We are going to use this equation everywhere in the calculations. You can forget my nice name, but don't forget this, please don't. Okay, so we can simplify and write EMF is equal to I into R plus R, where I is the current supplied by the cell of the battery, IR or the V is the terminal PD, and I small r is the lost voltage. Okay, now consider the circuit below in which a cell of EMF E and internal resistance R is connected to an external resistance R. This is an external resistance. This is a voltmeter. This is an ammeter. You are well acquainted with these symbols. Look at that. First pause and look at this diagram properly. Okay. So when the switch is closed, the voltmeter reads the EMF, which is E of the cell. And when the switch K is open, I hope I read that rightly. When the switch K is open, when it's still open, the voltmeter reads the EMF of the cell. And when the switch K is closed, the voltmeter reads the terminal PD of the cell. It's observed that V is less than E. The terminal PD is always less than the EMF. What did we say is the name given to the difference between the EMF and the terminal PD? Or EMF minus terminal PD will give you lost volts or lost voltage. So the terminal PD V equals to the PD across the external or the total external resistances. We've already discussed that. Now look at this experiment. It's so common. An experiment to determine the EMF and the internal resistance of a cell. There are so many experiments that you can use to determine the EMF and also to determine the internal resistance of a cell, but I've just picked out one. You can pick yourself a copy of the Clarified Physics for Senior 4, written by our friend Mr. Semanda Francis and Mr. Gutu Duncan and Mr. Okun. It's a very good book. It will explain all the experiments that can be used to determine the EMF and the internal resistance of a cell. I'm just going to look at one. Welcome back. So we were looking at the experiment to determine the EMF and the internal resistance of a cell. So we have here a cell, we have a switch, we have an ammeter, and a rheostat. These have to be arranged in series, and then in parallel we shall have to place a voltmeter. So let's arrange the ammeter, the rheostat, the cell, and the switch in series, and then we put a voltmeter across the cell. We connect it like that. Now the procedure is simple. First of all, we're just saying a cell, an ammeter, a rheostat, a switch, and a voltmeter are connected in a circuit as shown above. So with the switch K open, the EMF E of the cell is read. We can just say the EMF of the cell is read from the voltmeter and recorded as E. The switch K is then closed and the rheostat is adjusted so that a small readable current I is read and recorded from the ammeter, and the voltmeter V of the reading V of the voltmeter is obtained. Now look at this. When you close the switch, the rheostat is adjusted so that a small readable current, or the smallest readable current, you start with the smallest readable current, you record it from the ammeter, and then you also note the voltmeter reading. Then, with the switch case still closed, the rheostat is adjusted to obtain different values of I and V. I, this is the ammeter reading, and V is the voltmeter reading. So after obtaining the different values of I and V, the results are tabulated and the graph of V against I is plotted. The vertical intercept of that graph will give you the EMF. Now this EMF must, if you compare with what you obtained before closing the switch, it must be, they must be similar actually. Now this is from the graph. The other one was just before you closed the switch. So from the graph here, you know the intercept is the EMF. And the slope S of the graph is obtained. Now the slope is negative and the internal resistance R is obtained from R is equal to negative S. So the negative value of the slope will give you the internal resistance of that cell or the battery. Now look at this. Let's have a graph of, we have two axes here, a graph of V against I. On the vertical we are putting V in volts. This is the voltmeter reading in volts. On the horizontal we are putting the ammeter reading in amperes. And so we plot a dot and a circle, a dot and a circle, a dot and a circle. We have here different values. Draw the line of best fit through them and also get the slope here. We all know how to obtain the slope. So the slope is negative R, and therefore R will be equal to negative S. We have already looked at that. And the intercept here we said gives us the EMF. Remember, the intercept here gives us the EMF, and for this to qualify to be the vertical intercept, the horizontal axis, the horizontal values must start from 0. You see that? Must start from 0 strictly. So let's look at the proof. Why do we conclude that the intercept is the EMF, and why do we conclude that the slope is negative R? We all remember this formula that E is equal to IR plus IR, or I into capital R plus small r. Remember, this is the total external resistance or the effective external resistance. This is the internal resistance. So we can write it this way. It's the same thing. We know that V, this is the terminal PD. This is these are the lost volts or the lost voltage. This is the EMF, which we can rewrite as V is equal to E minus IR. Now look at this. If we rewrite it in this way, which is in the form Y is equal to MX plus C. So if we plot V on the vertical axis and I on the horizontal, if you remember, Y is equal to mx plus c, which is the equation of a straight line. This takes the place of y. The I takes the place of x. That means we put on the x-axis. Y is on the V is on the y-axis. If y is equal to mx plus c, so you realize that the y, our y, is occupied by V. Our m, which is the slope or the gradient, will be negative r if x is occupied by I. And the intercept here, the vertical intercept, is going to be the E, which is the EMF. So where the slope or the gradient S is equal to negative r and the vertical intercept is the EMF E. Let's look at this example, which was a revision question, and actually I want you to do this. In 2003, they asked you, paper 2, a cell is connected in series with an ammeter and a variable resistor. The potential difference V across the resistor varies with the current I supplied through the resistor as shown in the graph below. N is missing. So use the graph to determine Roman 1, the EMF, Roman 2, the internal resistance of the cell. Look at this graph. This is the graph. Please, you can pause and study it. Remember, Roman 1 requires you to get the EMF, and Roman 2 requires you to get the internal resistance. If this is a graph of V against I, we say that the vertical intercept here gives us E for as long as it starts from 0. And the gradient gives us, the gradient is the same as the slope, gives us the value of, the slope is equal to negative r. So to get r, you get negative of that slope. You get a slope times negative 1. So let me magnify a little so that you can see better. So I think you can all be able to read the intercept here. Please record down and send to me the value of the EMF, what you've seen, and also use this magnified value. I use this point and this point to give you points that you can use to determine the slope. Determine this slope and use it to get the value of the internal resistance. Okay, now let's look at arrangement of cells in circuits. Previously we looked at arrangement of resistors. Let's also look at how cells are arranged in circuits. Like resistors, cells are also arranged in series or in parallel. That's just easy. And I want to dive into the series arrangement, where we are considering 3 cells, each of when they have EMFs E1, E2, and E3, and the internal resistances are R1, R2, R3. This is one cell, another cell. So there are 3 cells. 3 cells here, arranged in series. In series, you just connect end to end. Here, these are their EMFs and the respective internal resistances. Now, the effective EMF is just the algebraic sum of the individual EMFs of the cells. I said algebraic sum. That means you consider how those terminals are connected. Yes. So E is equal to E1 plus E2 plus E3. Just add them, but bearing in mind how they are arranged. The effective internal resistance is just the sum of the individual internal resistances. So, in this case here, we shall have that R, the total internal resistance, is equal to R1 plus R2 plus R3. Just add them together. Now note, each of the cells in series arrangement supplies the main current I. Hence, they are more drained, leading to a lower lifespan of the cells. If cells are arranged in series, they don't last for long because they are drained, since they all supply the same current. They supply the same current I. Now, both the EMF and the internal resistance here will increase. The EMF increases because it's a sum, and even the internal resistance increases. Let's look at a few examples. Number 1, find the effective EMF and effective internal resistance for each of the following cells arrangements. Part A. Part A, we have cells arranged in series. We have here part B also, they are in series. But now look at part A. Part A, we have a positive terminal, negative, positive, negative, positive, negative. Part B, we have positive, negative, but here there is a change where this is opposing these two. Let's look at the given EMFs and internal resistances. So we have here 2 volts, 3 volts, and 4 volts. Just add the effective EMF here is going to be the sum of these ones. So you're going to add the 2 plus 3 plus 4. And for this case here, the total internal resistance is going to be 0.5 plus 0.5 plus 0.5. So the effective EMF will be what here? If you add 2 plus 3, what do you get? That is 5. Then plus 4, you have 9. So the effective EMF is 9 volts and the total internal resistance is 1.5. Now look at part 2, or part B, sorry. Here you will have 2 plus 3, because these are arranged in the same way, to give you 5, minus this one which is opposing. So you will have 5 minus 4, giving you 1 volt. The effective EMF is going to be 1 volt. And here, the effective internal resistance, the internal resistance has no arrangement, has no order. So for it, you just keep adding. So it will remain 1.5. Okay. Now, number 2, two cells, each of internal resistance 1 ohm and EMF 2 volts are put in opposition. That's the opposition series arrangement in a circuit. Determine the effective EMF and the effective internal resistance. Now remember, these are two cells. They have the same internal resistance and they have the same EMF, the two cells. To determine the effective EMF, because the two are in opposition, this is what we mean. They are going to be arranged. One cell is like this and the other is like this. This is what we mean by opposition arrangement. So they are arranged like that. This one has to connect, yeah, like that. This is, the EMF is 2 volts, even this one 2 volts. Internal resistance 1 ohm, even this one 1 ohm. So the effective EMF here, E is going to be 2 volts minus 2 volts, because they are opposing each other, and you're going to end up with 0 volts. Then the effective internal resistance, for it has no internal resistance, is resistance is a scalar quantity, it has no direction, so there is no need to consider the signs. So we shall have 1 ohm plus 1 ohm, giving you 2 ohms. Okay, let's proceed. Now part B asks you, does current flow in such a circuit? Please, you must find out the answer to that. Honestly speaking, when the EMF, the effective EMF is 0 volts. So what do you think? So what's the parallel arrangement of cells? We have cell 1, cell 2, cells 3 arranged in parallel. Remember, we said for parallel arrangement, these cells must be arranged between these 2 points here. So we have the EMF of the first cell is E1, its internal resistance R1, and for the respective cells, they are also arranged that they are also denoted that way: E2, R2, E3, R3. So the effective EMF is just the average of the EMFs in parallel. And in most cases, for O level, they give you when they are equal, all of them, they are equal. So the average of equal EMFs will be just the EMF of 1. So we are saying if the EMFs here, E1, E2, and E3 are equal, then the effective EMF is the EMF of just one of the cells. The effective internal resistance is given by the formula. You know, those will be resistors in parallel. You get the reciprocal. The reciprocal of the effective internal resistance is equal to the sum of the reciprocals of the individual internal resistances. And when there are only 2 cells in parallel, then you go back to our formula here. R is equal to R1, R2 over R1 plus R2, which is the same as prophets up and judges down. You understand? Okay, I hope you are not offended. Product over sum in simple terms. Note, for parallel arrangement of cells, Roman 1, the effective EMF does not increase and does not reduce. So it's just the same. So the effective internal resistance reduces, yeah, and the cells last longer. This is a very big advantage. You look at this. The effective EMF does not increase. So if you're using cells of 1.5, if there are 3, 1.5 volts each as the EMF, the effective EMF will be 1.5. But the internal resistance will reduce and the cells will last longer. Examples: find the effective EMF and the effective internal resistance for each of the following cells arrangements. These are 3 cells. Let's put them in parallel, connected between these 2 points, this point and this point. Now, what is the effective EMF here? What's the effective EMF? If you remember, how do you get it? This 1.5, 1.5, 1.5. Remember, we said if devices are in parallel, the voltages across each of them has to be the same. Therefore, the effective EMF is just the EMF of one of these cells, which is 1.5. And what is the effective internal resistance? Let me just have a place for writing. Here we say 1 over R is equal to 1 over R1 plus 1 over R2 plus 1 over R3, which is going to be 1 over R is equal to 1 over 0.5 plus 1 over 0.5 plus 1 over 1, which is same as 1 actually. So 1 over R will give you, this is 2 plus 2 plus 1, which is 1 over R is equal to, that is 5. When you cross multiply or you get reciprocals, 1 over R is equal to 5 over 1. Therefore, this means that R over 1 is equal to 1 over 5. 1 over 5 is the same as 0.2 ohms. So you see that in this case here, our effective EMF, our effective EMF here is equal to 1.5 volts, and our total internal resistance or effective internal resistance is 0.2 ohms. You see that this is very small. The internal resistance has reduced, but the EMF just remains just the EMF of one of the cells. Number 2, if you have two cells in a parallel, they all have EMF 1.5 and internal resistance 0.5, and they are connected in parallel. So what do you do here? Remember, the effective EMF is going to be 1.5 1.5, and the internal resistance here, the effective internal resistance, since there are two resistors in series, so here we can just use our formula, which you can use 1 over R is equal to 1 over R1 plus 1 over R2, which you say 1 over R is equal to 1 over 0.5 plus 1 over 0.5, which will give you 1 over R is equal to 2 plus 2, which is 1 over R is equal to 4. Therefore, R is equal to a quarter, which you write as R is equal to 0.25 ohms. But on the other hand, you can use our formula. R is equal to the product, which is R1 times R2 over the sum R1 plus R2, which will be R is equal to the product, that will be 0.5 times 0.5 over 0.5 plus 0.5, which will give you R is equal to 0.25 over 1, which is 0.25 straight away. Okay, now more examples. A cell delivers a current of 0.5 amperes when connected to a resistor of resistance 2 ohms. If the EMF of the cell is 1.5, find its internal resistance. I want you to remember this formula here. We have been given here EMF is 1.5, the current flowing is 0.5, the external resistance, total or effective external resistance is 2 ohm. They gave us just 2 ohms. There are only 2 ohms. There is only one resistor of resistance 2 ohm, and the internal resistance is not given. So remember, E is equal to IR plus IR, I capital R plus I small r. This is the terminal PD this is the lost voltage. So you can substitute here in this formula and you end up with internal resistance as 1 ohm. Going to the second example, they said in the circuit diagram below, the battery has an EMF of 3 volts. Find the internal resistance R of the battery if the current of 0.6 amperes flows. Now, can you do that? Okay, maybe let me do this as the last one. First, summarize what is the EMF given here. The total EMF, remember there are 3 cells, there are 2 cells, and to make a battery 2 cells, that means each one of them is 1.5 volts. These are common dry cells, as you know. So we have 3 volts, that's our EMF. The total external resistance, do you know it? But they gave us I as I is equal to 0.6 amperes. So you need capital R, which is the total external resistance. These are 2 cells in parallel, two resistors, sorry, in parallel. We shall have R1, R2 product over the sum. And that will give you capital R is equal to 4, that is 2 times 2 over 2 plus 2, which will give you 4 over 4, which is 1 ohm. Okay, now remember EMF is equal to IR plus IR. Yeah, IR, sorry, this is supposed to be a small r. This is wrong. It is E is equal to IR plus I small r, which will be E is 3 volts, will be equal to I, that is 0.6 times R1 plus I, which is 0.6 times small r. Yeah, so you can use this to get the value of small r. Get me the answer, please. These are yours now. Okay, you pause and do the questions. Even this one is yours. Even that one. Now I will stop here for now before we go into further questions. Ask yourself here, are these resistors in parallel or they are in series? We shall continue from here. Thank you so very much for those of you that are always endeavoring to do these questions on time and submitting them for marking. I pray that God blesses you and gives you the grace to continue studying. And I know you're going to score a D1 in physics in your UCE exams 2020. I wish you the best of the day. May God bless you. Bye-bye. I remain the one and only Mr. Mandy Gaines, Selma Christian High School.
Emma, come on. Time to revamp some music. If we live out to you, Father, the creation that I grown